In this problem, we have a horizontal line of charge lying on the x-axis, starting from the origin, extending towards the positive x direction. The total charge on the line of charge is capital Q, it's positive, and the total length of the line is capital L. We'd like to find the electric field created by this charge distribution on the x-axis at a random point on the x-axis where x is greater than capital L, meaning in this region to the right of the charge distribution. Let's start by marking a point P on the x-axis like so. So we'd like to find the electric field created at the point P due to the linear charge distribution. Point P is a random point on the x-axis. Now, of course, point P is a certain distance, at a certain distance from the charge distribution. For instance, we can mark this distance here, starting from the right end of the line of charge all the way to point P, and I'm going to call this distance lowercase d. So d here is a constant. It's the distance between the right end of the linear charge distribution and point of interest P. Now, what will the electric field look like at point P? Remember, electric field is a vector quantity, so we should think in terms of magnitude and direction. And so the line of charge is a charge distribution. It's an extended shape. What kind of field is it going to create? We can try to imagine that by splitting the charge distribution into small pieces. Now imagine dividing the line of charge into small pieces such that each small piece will act like a charged particle. Okay, so for instance, here's such a piece, and I'm going to call this one dq. It has charge dq. It's at a certain distance from point P on the x-axis. It's going to create an electric field at point P, pointing away from itself because the charge here is positive. So dq is a point charge creating an electric field at point P away from itself. So then the direction of the electric field due to charge dq at point P will be in the positive x direction. So this is what it looks like. I'm going to call this vector dE. So dE is the electric field vector due to point charge dq at point P. Now, there are many point charges like dq. In fact, there's an infinite number of point charges that make up the linear charge distribution capital Q. So to find the total electric field at point P, we need to add up all the electric field vectors due to each of these point charges dq. And what does that mean? That means we're going to take an integral basically. So how should we do this? Because these are vectors, right? You don't add vectors easily in general, but in this case it's going to be actually easy because all the vector dE's will be in the positive x direction. So all of those electric field vectors will be horizontal. They only have an x component and they will point in the positive x direction. Therefore, we can express E, the total electric field, the magnitude of the total electric field at point P, as the integral of dE, dE being the magnitude of the electric field due to each point particle dq. So note that I have dropped the vector notation at this point because all of these vectors lie on the x-axis. They only have x components and their x components are equal to their magnitudes. So we just take an integral over dE to find the total or net electric field magnitude at point P. Our next task is to come up with an expression for dE, right? We can't just take this integral right now. It's like a symbolic formula as of now. Now, how should we do that? Well, remember, dq is a point particle, so let's just apply the point particle formula for the electric field at some distance from the particle. So how do we do that? Well, the electric field magnitude due to a point charge, is proportional to its charge, which is dq here, divided by 4 pi epsilon 0 times the square of the distance between the point charge and the point of interest. Basically, the distance right here, this distance, is what should go into the denominator, right? The square of this distance, all the way from dq to point P. How can we express that in terms of the given variables and also potentially in terms of x, which will be our integration variable in this problem? So if you think about it, this distance here is capital L plus D minus this part, right? And this is basically just x. This is the position of dq along the x-axis. So this is my variable x. So then the distance that should go into the denominator is capital L plus D minus x. And remember, we need to square it like so, squared. Can we take the integral yet? Well, not really. Take a look at this expression. It has dq in it. We can't really integrate over dq. So let's think, as dq changes, what variable changes? Imagine other point charges along the x-axis like this, right? That make up the line of charge. Well, each point charge has a different position x. So x is what changes as we move from one side of the linear charge distribution to the other side. So x will be our integration variable. Our next task then is to express dq in terms of dx. So how do we do that? Let's actually focus on dq a little bit, like this. What is this width? Well, it's the infinitesimal displacement along the x-axis, so this is really dx. How can I express dq in terms of dx? At this point, let's introduce the linear charge density, lambda. How is lambda defined for a line of charge? It's basically total charge, capital Q, divided by total length of the line of charge. So capital Q over L is the linear charge density of this charge distribution, right? But lambda is also equal to, if you think about the dq, the small piece dq, we can apply lambda to dq as well, because this charge distribution is uniform, so charge density is the same everywhere. So lambda is also equal to dq divided by dx. The total charge on this small piece divided by the width of this small piece. Combine these two expressions to eliminate lambda, which is a variable we just introduced, so we're going to get rid of it. So set the right-hand sides equal to one another. What do we get? We get capital Q divided by L equals dq over dx. Now let's rearrange this expression and isolate dq. What do we get? dq equals capital Q over L times dx, like so. Q over L times dx. Now let's apply this. Let's go back to our integral expression and substitute for dq. So what I'm going to do next is to rewrite this expression with dq substituted with capital Q over L times dx. Here I have the integral expression with dq replaced. At this point, we can also set the lower and upper bounds of our integral. Let's take a look at the picture again. Along the line of charge, x runs from 0 to capital L, so those are the lower and upper bounds of our integral. In the next line, I'm going to move the constant variables outside of the integral sign, and then we'll take the integral. Here is the result of the integral. So the integral part is fairly straightforward. You can imagine doing a u substitution where u is equal to L plus d minus x. In that case, du will be negative dx. And the final answer is right here. The magnitude of the electric field at point P is equal to capital Q over L times 4 pi epsilon 0, parentheses 1 over d minus 1 over L plus d. Note that our final answer is in terms of all the given constants and the problem. Now, what is the direction of the net electric field vector? Remember, all the electric field vectors, dE vectors, point in the positive x direction, so the net vector also points in the positive x direction. We can use the unit vector notation to express the net electric field vector at point P, because it points in the positive x direction. Vector E is equal to its magnitude times I hat. Next, we place a point charge on the x-axis at the position of point P, and the point charge has charge lowercase q. The question is, what is the direction and magnitude of the force that the line of charge exerts on the point charge? To answer this question, we can use the connection between electric force and electric field. Force acting on the particle or the point charge is equal to its charge times the electric field at the location of the point charge. So really all we need to do is to multiply this expression by lowercase q. Here's what we get when we do that. Next and last question is, what happens to F when D becomes much greater than capital L? In other words, the distance between the line of charge, capital Q, and the point charge becomes very large. To see things more clearly, let's actually rearrange this expression a little bit. I'm going to rewrite the expression in parentheses. I'm going to cross multiply and actually add the two fractions together. So if we bring these two to a common denominator, the denominator will be d times L plus d, and in the numerator we'll have L plus d minus d, like so. So this is the expression in parentheses. We have an I hat right here, and outside we have capital Q, lowercase q, divided by L times 4 pi epsilon 0. This can simplify even further. Take a look at the denominator in the parentheses. These cancel. Sorry, take a look at the numerator in parentheses. These cancel, and we have capital L left in the numerator, which cancels out with the L in the denominator. So we have a placeholder 1 remaining in the numerator inside the parentheses. And let's take a look at the denominator. We have d times L plus d. If d is much greater than L, we can replace this approximately with just d, right? Because capital L is much smaller. So the denominator goes to d squared, basically. In other words, so here's what we get. F becomes equal to, or F goes to, the product of the two charges divided by 4 pi epsilon 0, because capital L's canceled out. And then in the expression parentheses, we have 1 divided by d squared. Does this look familiar? I hope so. This is the formula. This is the Coulomb force, basically. The force between two point charges. Does it make sense? Well, yes, if the point charge lowercase q is very far from the line of charge capital Q, the line of charge acts like another point charge. That's why the expression for the electric force between them reduces to the force between two point charges.